All right. So welcome back after the exam, which everybody clearly enjoyed a lot as they were leaving. I guess that one got a little long. It had a couple of bugs in it. Sorry about that. If you remember where we were from last time, I wanted to pick up and try to get some distributed topics in here toward the end. Possibly this will help a little bit with understanding your project. But for starters, if you remember way back before the exam, so that was a week ago, we were talking about two-phase commit, which was the first of several sort of distributed things we talked about. And it's a distributed transaction, and it's a way for two or more machines to agree to either do something or don't do it, and do so atomically. And two-phase commit is described typically with one coordinator and workers. And the algorithm basically is that the coordinator asks the workers if they can commit. And if the workers all say, yes, commit, then we commit. Otherwise, we don't. And the key thing about this particular algorithm is the way it uses a log to help recover if anybody fails in the middle of the transaction. Were there any questions about two-phase commit? Now, of course, nobody actually uses two-phase commit in the internet as a whole. In the wild, they basically use other options like Paxos is a good example of something that's a lot more failure tolerant. And if you were to take my grad class, we talk a lot about Paxos and so on. But anyway, and also notice, by the way, the other interesting thing about this is who's the coordinator, right? So these algorithms all have a leader election aspect to them where you have to decide which of the many nodes that you have participating are actually going to be the leader, and that's part of the process. So that's where this really gets interesting. Now, before we go into more distributed topics such as storage, I wanted to say something a little bit about remote procedure calls. Do they talk about this in 61C at all? Okay, good. So raw messaging, you can obviously build anything out of raw messages. I mean, bits are bits. And, you can open up a TCP channel or a UDP connection and figure out at the source how to wrap your information up and at the destination how to unwrap it, and you can have communication. But the question you might ask yourself right away is, why reinvent the wheel? Is that still too loud for everybody? My brain is echoing here a little bit. Why reinvent the wheel? And in fact, there's really no reason to do that. There's many instances of things called remote procedure calls. And the idea is very simple. It's call a procedure on a remote machine. Now, what does that really mean? That means that we're going to somehow take the arguments and wrap them up and send them off, and on the other side unpack them and make a procedure call in a way that is hopefully somewhat transparent to the person that's writing this code. Okay, and that's what a remote procedure call is. And so, for instance, the client might call this, remote file system method read argument rutabaga. And what happens is it's translated automatically to a call on the other side into file system read rutabaga or whatever. And the trick about the remote procedure call environment is it makes it really easy to do this. So the programmer on the client is basically writing a procedure call, and as far as they're concerned, and somehow communication happens underneath the covers to make this procedure call, and the result is returned back to the client, and it all just happens as if you actually made a local procedure call. Okay? And so how is this implemented? So there's obviously message passing under the covers. Typically, and I'll show you this graphically in a second here, but typically there's something called a stub, which provides glue at both the client and the server. And the client stub is the thing that basically marshals arguments, turns them into bit strings that can be sent off to the server, and the server stub unmarshals the arguments and then, of course, marshals the return values. And this word marshalling is a useful one to get a hold of, which is basically converting values into some canonical form that can go over the network. This probably involves making everything, for instance, big endian integers and so on, so that it's universally understood no matter what the server is. Okay, questions? So here's a good example. So we have two machines. Let's say, for instance, A is a client and B is a server, just for the heck of it. So client has some program, and it makes a call, a procedure call, and that procedure call is really into a stub that gets linked in with the client code. And so that procedure call stub actually takes all the arguments, bundles them up, and turns them into a message which it can send through some packet handler portion over the network. And notice how I've got a little mailbox notification here. So typically you have to set this up at the beginning who your remote destination is. And this mailbox is probably something like an IP address and a port that you've gotten through some name service. That packet goes to the server-side stub, which unbundles the arguments, and the server stub makes a procedure call to the server, and so server code, and this server code doesn't necessarily have to even know that that's coming over the network. So both the client and the server are in the dark in some sense that there isn't communication there. Now, how would they know that there was actually communication there? So they're probably not going to be completely in the dark. What are some things that they could be aware of? Yeah. Yeah, latency. Okay? Like failures, like any number of other things, right? Latency is a really big one though, right? And so this procedure call gets returned, the arguments are rebundled, and then they'll be sent back to a second mailbox, which is the one set up for returns, which then get unbundled at the client and so on. So this information flow is actually sending messages over the network, but as far as the code abstractions or APIs are concerned, the client and the server is able to mostly ignore the network. Okay? Questions? All right, so, you could easily come up with how this is equivalent to a regular procedure call. So the parameters that are in the initial request are part of the request message. The result is a reply message. The procedure name gets passed in the request message. The return address on the stack is really turned into a mailbox and so on. The interesting part about this, though, is that every RPC system that you're likely to use has a stub generator, which is a compiler that generates that stub code for you automatically. So you don't have to write that code. And what it takes as input is definitions in an interface definition language, or IDL, which contains things like, well, what are the types of the arguments and the return values for the procedures I'm going to call on the server, or that the server is going to be called return to the client, whatever. And the output from that compiler is stub code to be linked on the client and the server. So you write this IDL, which describes your procedures, then you run it through the compiler, you get out some library code that you link on the two sides, and then you're good to go. Okay, and there's been a lot of work. I mean, RPC's been around for 20 years plus, 25 years, and so basically it's pretty mature science, and although there are many, many different types of RPC systems. But for instance, there are some cross-platform issues that the RPC system handles nicely. Like, for instance, the client-server are different architectures or languages, or have different endianness or whatever. And typically, things like every item gets a platform-neutral encoding of some sort. And the best example that I can give you guys, having come through the 61 series, is integers are in different orderings on different types of machines, and the standard network ordering is typically big endian, and so these RPC systems always convert everything into network format, which is big endian. Okay. Questions? Good. Now, how does the client know where to send things to? So typically there is a name service, so you got to translate the remote service into a network endpoint, just like we use DNS. This is a binding process, and often the RPC environment has with it a binding server that's part of the process. So dynamic binding being the simplest thing. Most RPC systems have a way of turning the name of the service, like I want to use NFS, or I want to use a certain service, into the actual IP address and port. And why do it dynamically? Well, then we can do things like catch access control failures, like we can refuse to even translate. We can decide if a server fails, how to fail it over to another server, and so on. And if there are multiple servers, we can do load balancing. So there's lots of useful things that we can do there. Okay, and notice, by the way, that this idea works perfectly well if there's lots of clients, because the clients are each sort of passing where their return mbox is as their outgoing request. So a server can handle many RPCs from many different clients, and it all works well. Okay? Questions? Now, the problem with RPC is it's not a procedure call. And so there are obviously all sorts of non-atomic failures, so different failure modes in a distributed system than if we were just linking procedures. You can consider many different types of failures like address spaces crash, kernel crashes, compromised machines, and so on. And before RPC, the whole system crashes, and so maybe that's a good failure indicator. After RPC, one of the many machines that are involved might crash, and you can get much more subtle errors like consistency problems. And so, by the way, in the end of the term here, we are now moving off of the one single machine into the many machines, and that's where these interesting failure modes become a problem. Okay, or the opportunity for the great distribution shows up, and you have to be a little careful. Maybe I should say it that way. You can easily get an inconsistent view of the world if certain things fail that weren't expected to fail, and we'll talk a little bit about consistency several different times throughout this lecture. And so one answer, of course, is to do some sort of distributed transactions to know that you've got enough things that actually committed. If you're really worried about maliciousness, last time we talked about Byzantine commit protocols and the Byzantine generals problem. If anybody here is ever interested in actually implementing a Byzantine agreement protocol, talk to me. I'll be more than happy to point you to papers that are not exponential in the number of nodes, because that's a pretty inefficient way to go. And of course, performance was the thing that was really brought up right away. That was a great observation. The cost of a procedure call is very much less than the cost of, say, doing an RPC on the same machine to another process, and is very much less than a network RPC. And so typically, although the programmer writes the code transparently without knowing there are things there, they do, and that's that word transparent, by the way, which really means opaque. Everybody caught that from a couple of times ago, right? Without actually having to know about the network being out there, the programmer still typically has to be aware they're using an RPC system because they've written the IDL code probably, or maybe they've used somebody else's, and they've got to deal with failures. Okay. So that's all I'm going to say about RPC. I wanted to make sure we brought it up because it does underlie a lot of the way people program distributed systems. There are RPC systems out there. And I think I mentioned a bunch of RPCs. Well, I'll get to that in a second. There are many systems. But so for instance, now that we've brought this up, if we have different address spaces, think different processes communicating with each other, how do they talk to one another? Well, we've all talked about, beginning of the term, we talked about shared memory with semaphores and monitors, and then we've certainly talked about the file system, and pipes or sockets, basically. So these are all ways that different processes can talk to each other. But you can also do a remote procedure call from one process to another. Okay? Why not? And it's certainly perfectly fine. And RPCs can be used to communicate between address spaces on either different machines or the same machine. So the cool thing about that is I can start out with everything running on one machine, and if it's too slow, I can just migrate something off to another machine, change the binding, and now transparently that one service that was running locally is now running remotely, and I've load balanced without changing the code. All right. And oh good, I did put this in here. There's lots of RPC systems. These are just a few. Corba, you've probably all heard of DCOM if you're Apple folks. RMI was a Java version, and so on. All right. So here is my brief mention of microkernels. So microkernels were sort of a new architecture in the purest sense 30 years ago, and the idea was very simply that rather than what we've been talking about mostly in this class, where everything is in kernel mode and then you have applications running on top, what you do instead is the thing actually running in kernel mode is a very small set of things. They're something that supports threads and address spaces and an RPC system, and then everything else is running as user level in its own address space. And so not just the applications, but for instance, the file system. You package it up as a user-level process. It runs on top of the microkernel. And how does somebody perform an open to the file system? Well, they do an RPC to the file system. Okay, and then the file system does an RPC back with its results. All right, and what's the advantage of this sort of microkernel structure? Yeah. Yeah, so you could easily put in a new file system. That's good. Or, what I mentioned before is if the file system's taking up too much of your CPU, you could move it to another one in a cluster or something. So it's very, very mobile. What's the disadvantage of this, do you think? Yeah.
It's slow.
Yeah, so it's slow is a really good first approximation. In fact, this is what killed the original Mach kernel probably it was slow. There's been a lot of work in the last probably 10 years on things like L4, which is a kernel that is quite fast and is sort of in the best traditions of microkernels, and it's pretty good. But it's specialized, okay? And so I think the slowness is pretty clear here because you're crossing address spaces, and it started out being really slow. It's just not as bad as you might think. And so I think other reasons that you guys haven't mentioned is the why to split things up. You get fault isolation, which is nice because bugs are more isolated. You force modularity because only the RPC interfaces are the ones that are exported, as opposed over here, you call into a random procedure in the middle of the file system because you know it's there and you've been reading the code. Okay, so this kind of system is, and look at Linux source code someday. If you haven't done it yet, it's an eye-opener as to how badly designed many of the interfaces are. And the reason is everybody can read the code, so they call whatever they want. Okay, now I'm not saying that this is always the best alternative, but it does kind of enforce a good interface design up front. Okay, and then location transparency, you can move things around. Okay, that's all I'm going to say explicitly about microkernels. Are there any questions? What's the microkernel of the 2010s? So L4 is a good microkernel that literally fits this model, but does anybody know what people who have a tendency to like microkernels for these advantages I mentioned are thinking about these days? Say it again? Herd. Okay. Can we be more, less specific? So basically, in general, virtual machines are ways of basically dividing up your spaces. And if you program them not by putting whole operating systems in a virtual machine, but rather put little components in the virtual machine and you use the protection of the virtual machine, you can get something very much like a microkernel. And if you look at a lot of what people are doing with Zen these days, there's some pretty cool microkernel-like things that make a lot of sense today. And if people are interested, I'll mention in my last lecture a little bit later during the Administrivia, but maybe we could do that as a topic. They're called unikernels, which are kind of fun. So there is actually a lot of work in the microkernel domain, but it's sort of tending a little bit more toward using virtual memory pieces, or virtual machine pieces. Okay, questions? So let's talk now. We're going to stop talking generically about distributed decision making, and I want to talk about storage, because storage is a pretty important topic. And network attached storage in general, the idea is kind of you got a bunch of disks or whatever, SSDs that are somehow in the middle of the network, and you're accessing them over the network. So it's network attached storage. Hopefully that's not entirely surprising. And there are several things you can worry about in this environment. One, you can say, well, changes that I make to my data that somebody else might view should be available to everybody, and they should sort of be available in the order in which they're written. That's kind of a consistency argument. Another thing is availability. Wouldn't it be nice that even when parts of the network get partitioned or servers crash, that I can still get at my data? Okay, and a third one is partition tolerance, which basically says if I were to draw an arbitrary slice through the network, it'd be nice if the system kept working. So it's tolerant to partitions of the network. Okay, and this is not entirely an accident, CAP. All right, and so consistency, availability, and partition tolerance, or CAP, is this notion that you cannot have all three at the same time. Now, this is sometimes called Brewer's theorem, for Eric Brewer, who sort of voiced it more like Brewer's hypothesis back in the early 2000s when he had the caching company Inktomi search company. But there was actually a follow-on whole issue on looking at various versions of Brewer's theorem. But the bottom line here is you cannot actually simultaneously have consistency, availability, and partition tolerance. Okay? So if you thought you were going to build the perfect distributed system that could deal with network partitions, was always available and perfectly consistent, you're going to go home tonight disappointed because it isn't going to happen. Okay? Question? Yes. You know, there are proofs for, this is a little too loose and nebulous, but there are proofs for things that are pretty close to this. The trick is you got to actually be much more precise about what you mean by these different things, and then there are proofs. There was actually a whole issue where a bunch of theorists kind of wrote about this idea in general, and there was a lot of different proofs in there. But yes, you can prove something essentially like this if you're willing to be much more precise. Yes?
In the same serial order, what does that mean exactly?
So what it means is if I write A and then I write B, everybody else is going to see that I wrote A and then I write B. They're not going to see that I wrote B and then A. And this is actually a pretty important coherence issue that shows up, and they talk a lot about this when you talk about cache coherence in like 152 and so on. But good question. Okay, so let's talk in general about what a distributed file system might look like. So the idea is you have a client and a server. That's not entirely surprising, but the client says read and the server says data. Okay? You want me to explain this to you guys again? So the client says read and this, okay. So the idea is simple. The devil's in the details, right? But what is a distributed file system? It's something which gives you transparent access to files stored on a remote disk. All right? Which means basically that you don't have to know that it's on a remote disk. And naming choices start coming up right away, which is how does the client name the files? And one thing you could do is, for instance, say, well, I could name which server it is and what its local file name is. So I could make an explicit naming choice. And the problem with this, of course, is you can't move the files around. It's pinned to that server, and you're pretty much in trouble. But kind of when you mount an NFS file system or whatever, you're kind of doing this because you're sort of saying, I know what the server IP address is. I want to talk about files there. Now, however, when you actually mount, rather than putting the explicit host name into the way you name the file, the nice thing about mounting is you're actually doing the name resolution separate from the access. So for instance, here, coeus:/su, if I mounted it to this part of my tree, then what this means is if I talk about /users/su/whatever, I can talk about that file independent of what server it's on, and this will get transparently redirected to that particular server. All right? And so mounting is actually better than explicitly putting an IP address in all your file names. Okay, because what you're putting in here is sort of /users/su/fu. Has anybody actually dealt with mounting remote file systems before? Are there any administrators? Okay, or if you have a Windows box and you mount things, then typically the file name is u:/whatever, but that's the same idea, where the translation of coeus IP address happens during the mounting process, and then all of my accesses are independent of the actual location of the file system. So that's a little better. Now, even better is a single global namespace. All files in the world are somewhere. Okay? Slash, North America / United States / California / Berkeley /. There, you really haven't said anything about where the files actually are, but you do have a universal name in which to name them. Now, I know that sounds a little, I don't know, how many people think that sounds like a nice way of naming things? How many people think that's a little excessive? Anybody? Okay, how many people don't have an opinion on this? Okay, a couple of you. So it turns out there's a system I'm going to tell you about in a little bit called AFS for the Andrew file system that actually did have a single global namespace. And it was kind of cool. Okay, you could name every file in the world that was in AFS. What's a little unfortunate about it is it doesn't scale too well because the world is really big. Okay, and just imagine the problems you're having with your 3 terabyte drives that you have a lot of stuff on, finding things there, and then imagine that you really got a file system name that spans the globe, and it gets pretty messy pretty quickly. Okay, so let's look a little bit about building a more distributed version of this where we have more than one client. Okay, so this is more realistic, and we'll put a cache here at this other side for the heck of it. But now we essentially have a remote disk where reads and writes are forwarded to the server, and then using RPC to make this easy. And then basically what we do is in the layer of the operating system dealing with files, we just translate things like open and read and write using RPC stubs into open, read, and write on the server. So it's very easy to imagine installing this into a file system. And then if we don't put any caching in, this gets really easy because we basically just turn every open, close, read, write into a direct RPC at the server side, and it comes back. And now we've got an easy system to talk about, right? Because everything's happening at the server file system, and all my client is doing is turning my system calls into calls to the server. Does everybody think that sounds pretty simple? I didn't say it sounded good, it sounds simple, right? How many people think that sounds like a pretty simple solution? Okay, it's just taking the system call level, turning it into a stub. Okay, so what's wrong with this? Why would you not want to do this? Well, for one thing, there's no cache here, right? I mean, that's a pretty big one. Anything else? Yeah. So every time you want to make a read, you have to make an RPC. So, yeah. Now, what's interesting about that is RPC is not necessarily high overhead, depending on how well it's done. But it is pretty high overhead that every read and write goes all the way across the network, which is getting us actually back to the caching question, right? So a lot of the problems with this have to do with caching. Go ahead.
Maybe if the server happens to be down, there's no redundancy here.
That's right. So if the server's down, there's basically nothing you can do. That's great because presumably when you did an open, you got a file handle from this one server, and so if the server goes down, there's no way any other server could replace that, because it wouldn't know what to do with the file handle, right? It'd have no idea where you were. Good. Okay. So the advantage is the server is completely consistent, so all reads and writes happen in the same order on the server, so the consistency is not a problem, and the performance is just basically bad. Okay? So going over the network's a lot slower than going to local memory. Lots of network traffic. It's not pipelined because every request goes all the way out, comes back before you can even return out of the system call. So this seems pretty bad. And the server's a bottleneck. So this seems simple, but probably not desirable. So one of the things we can do is put some caches in. Okay, so everybody catch that? Wasn't that fun? Okay, so there's caches in there. And now, don't you love animation? So the idea is we're going to use caching to reduce the network load somehow. And in practice, most of the clients are running operating systems that have buffer caches anyway, so we want to make sure we just use the buffer cache that was already there. And the advantage is if the open, read, write, close, whatever can be done locally, we don't even have to do any network traffic. So if the cache is hitting, we might be good. Okay, so for instance, here I'm doing read of F1. It's not in the cache, so we go all the way over to the server. We get it off the disk, and it gets cached in the server's buffer cache. It comes back, it gets cached locally. And we return V1, and we're good. And then when we do these subsequent reads, we get them really quickly. Does everybody see how quick that was? Ready? Everybody see how quick that was? Ready? Okay, so very quick. So that seems good, right? Now, some problems start coming up here. What about failures? So for instance, if I do a write and I only have it in the cache and that client crashes, I've just lost my data. So that's probably not a good way to do a write. Even though in principle, I could satisfy this client as having done the write once it's in the buffer cache. Remember, that's actually the solution we had in the local file system. Right? It could be written in the buffer cache. Well, we got to do something better than that. So in this case, we better write it to the server and get an ACK back and then get OK. And the nice thing about that, at least, is that if the client crashes, we didn't lose data. Now, notice that this says that writes have a round trip in them, and that could be bad from a speed standpoint, right? So there is a slowness to writes. And by the way, we're going to talk about NFS in a moment. The original NFS protocol, every write actually had to go all the way to the server and come back, which was a terrible performance bottleneck. Okay, so what could we do? We could do some combination where it goes into the cache, but it's pretty quickly pushed to the server. You can sort of see some variance on this, right? Okay. And of course, consistency is a problem. So notice what happens. See, we've got this cache scenario where client number 2 has actually written an updated version 2 of things. And what's interesting to this is the way we've got it set up, if client 1 goes and does a read, they still get value 1 back. And client 2 gets value 2 back. So this is probably not too good. Okay, because basically, client number 2 has never propagated its writes to client number 1 somehow. Yes, question?
Could you set like a timeout on the caches?
Yeah, so good. You're starting to think about solutions here, right? So consistency is a big problem, and there's clearly a trade-off between how out of date I am and how fast and well the cache works. That's kind of the way you were thinking about timeouts, right? Good. Okay, so, the other question here before we tackle that whole cache consistency problem, we might say, well, what if the server fails? Well, can the client wait until the server comes back up and continue as before? So you might imagine that the server crashes, and so some message I've got starts timing out, and then the server comes back up, and then I pick up where I left off. Maybe I could do that, but maybe there's state that's lost. So that could or could not, that might or might not work, right? And pretty much any data that's in the server memory but not on disk could be lost. If there's shared state across RPCs, it's lost. So for instance, how did I describe this earlier? You do an open, you get a file handle somehow from the server, and now if the server crashes and I continue to try to write to that file handle, it says, I don't know what you're talking about. That file isn't open. I just rebooted. Okay. And another interesting one here is about not just if the server crashes, but what about retries? So imagine you say remove file foo, but your message might be lost. But it actually showed up the server anyway, and so you say, well, I think it was lost because I didn't get any knowledge. You say remove file foo again as a retransmission. But now the server says, well, I don't know any file foo. Error. Right? So you got to be kind of careful at what level you're doing retransmissions, because this is a situation where you go to do the retransmission because you think that the request was lost. It was actually done, and the next time you try to retry it, you got a problem. So this is interesting. It kind of pushes us to wanting to maybe have protocols that are idempotent somehow, that I can keep doing them over and over again so that retries work. Or I want to put some sort of TCP/IP under the covers so that messages are delivered once and once only. All right. So in particular, one option is a stateless protocol. So the idea here is a protocol which all information required to process a request is actually in the request. And what's good about this is the server has no state about clients and can crash and reboot at will. And that seems like a goal. And we'll have to see whether we can actually come up with stateless protocols or not. And of course, if the client crashes, you might lose some modified data in the cache that hasn't been pushed out yet. All right. So when we start thinking about distributed file systems, we're really going to want to start thinking about failure modes as well. All right? Questions? Now, midterm 2 is actually in the middle being graded. We're going to get it as quickly as possible. I knew somebody was going to ask me, so I will preempt that of what about the other grades? I'm working on trying to get that answer, but I'm hoping that midterm 2 will definitely be done by the end of the week. There are already solutions posted if you want to look, so they're up on the website. You may not want to look, I don't know. That one got a little bit long again, sorry about that. But anyway, we'll hopefully get things back to you soon. All right. Final exam, looks like it's in Wheeler Auditorium. We're not actually going to be split up, so that's nice. That's a big place. It's 3 to 6, and it's on the 15th of May, the Ides of May, as it were. All material from the... That was a joke. But anyway, all material from the course, slightly more focused maybe on the second half, but in theory, you're responsible for everything. You can have 2 sheets of notes, both sides. I did see somebody with microfiche-style notes during the last exam going like this. I'm not sure whether that was useful or not. I guess if you can write it or whatever, you can bring it. You will need a dumb calculator again, so try to find one of those. Questions on the final exam? So you're only responsible for material that we cover by Wednesday this week. This is the last week of instruction, by the way. Do you believe it? You guys are all going, yay! However, we'll actually, I'll talk about this in a second, going to have one more sort of special lecture next Monday if you guys are interested. You should be working on Project 3. Anybody here who isn't working on Project 3, I don't know. I don't have anything to say about that. It's Checkpoint 1's due Wednesday. So Project 3 is moving along, I hope. You guys are the first to actually try the C version of Project 3, so I'm hoping that it's working. Does it seem to be so far so good? Okay, so far so good. It's good. Is it a sideways thumb or upscale thumb? Okay, good. All right. Good. Hopefully if this works out well, this will become a new project for this class. So, okay, so next final lecture a week from now is a freebie. Won't be on the final. But what I like to do in a class like this is I like to give people an option to actually send me topics. Okay, now presumably they have something to do with the class, hopefully. But I've actually had people say, well, Kubi, I know you do quantum computing. Could you talk about that? And I've actually talked about quantum computing in 162 in one of my final lectures. It doesn't have to be the whole lecture. But anyway, whatever you would like, you think there's a hole in the topic material, something you really wish that I would have talked about, let me know. Try to let me know by, say, Thursday. Otherwise, I'll just put together a set of topics. Yeah. Post a poll on Piazza. In addition to having, that's a great alliteration. Yes, we probably could post a poll on Piazza. Precisely. That's a good idea. Let's do that. Okay. By the way, I was sort of thinking about talking about the Internet of Things by default or whatever, if that if we don't have any other topics. But I'll try to accommodate as many of the interesting topics I can. We'll see what happens. All right. Questions? Yeah.
Like, I was a little confused on the framing of the course you gave us a spiral overview.
Yes.
Like, each topic had, like, for example, networking had, like, 6 lectures, creating had, like, another 6 or something.
Well, so I think the security. You know what? I didn't alter the numbers. So that was when classes were 3 classes a week at an hour each. I guess I didn't alter the numbers. Sorry about that. So, other questions? Yeah. Yeah. So you still don't have them back for Project One? No, I know. Yeah. All right. Yes, very soon. I don't know what the holdup is on Project One. I thought that was done, so I will find out. I don't know what the story is. Oh, by the way, Wednesday being the last class and all, we do our HKN survey, so everybody should come for that, please. We would like that. All right, I think that was all I wanted to say. Okay, so let's talk about an actual distributed file system called Network File System, NFS. Originally developed by Sun Microsystems. It has 3 layers. There's a Unix file system interface, which is completely familiar to everybody. Open, read, write, close, file descriptors. There's actually a VFS layer, which I'll talk about in a moment, which distinguishes local from remote files. And so this is a special plug-and-play layer, which you can plug in either local disks or remote disks, and the right thing happens. Okay, it's an interface between the system call interface and the world and the disks. And then there's an NFS service layer if we happen to be going over the network, which is the bottom layer of the architecture. Okay, and the NFS protocol uses RPC, the first one of the first ones actually developed that had an IDL in it called XDR. And basically it provides file operations on the server for reading and searching directories, manipulating links, etc. And among other things, it's got write-through caching, so modified data is committed to the server's disks before the results are returned to the client. So this is more of a statement about the original version of NFS. There's a little bit of pipelining that's now done that lets you get an acknowledgement back before it's fully written at the remote side. Okay. So one of the interesting things about NFS is it's one of the first ones that was stateless. So every request provides all the arguments you need to actually do execution. So for instance, if I want to read a file for a given I number at a given position, that actually goes into the message. We don't have a separate seek followed by read, okay? Because this first case is stateless, the second one isn't. Does everybody see that? So if I have to actually keep the server keep track of where I am in the file so that each read gives me a different result, that's not stateless, whereas the protocol is stateless. Okay? And as a result, by the way, in principle, NFS servers can crash and restart, and the client can pick up where it left off. And there used to be a way to mount NFS when I first started using NFS, which was called a hard mount. And a hard mount said, when the server goes down, wait until it comes back up and then return things. And the problem with that is servers, when they go down, they don't come up right away. And so your clients would be all locked up in bad ways. Okay, and so most people do soft mounts on NFS. There's no need to perform things like open or close because there is no state on the server side. Okay. All of the things dealing with file descriptors are all purely in the local portion of the NFS stack. Every operation is idempotent, so performing requests multiple times has the same effect as if you performed it once, and that's why we can crash and restart. The one funny thing, so reading and writing is easy because you just read and write blocks. If I write the same block over and over again, it's not going to change anything, or if I read the same block, hopefully it's not going to change anything unless somebody's changing it. But what about remove? And so NFS actually has to have a hack about remove so that if you retry remove and the file isn't there, it's sort of less, it doesn't give you the kind of errors you would get otherwise. It's more advisory. Okay. The failure model here is supposed to be transparent to the client system, and the question of whether this is a good idea or not is an interesting one. So like I said, it used to be the fact that servers went down, the system stayed locked up until the server came back up. Well, locked up literally meant you probably couldn't almost do anything because the system was locked up waiting for that server to come back. Whereas a soft mount, which is not quite transparent, is much better because you just get an error on the file system and you can keep doing what you were doing before. All right, so this is a great example where transparency is not always a good thing. Okay? It's a great example where transparency is not a good thing. It used to be that the only way you got the client out of that mode, by the way, is you actually had to reboot the client. So imagine the server goes down and the only thing you can do is to reboot your machine and then you're back up and working. Okay. Now, what about consistency? So it's a weak consistent protocol. So client polls the server periodically to check for changes. It polls the server if the data hasn't been checked in somewhere between 3 and 30 seconds, which is tunable. And if a file is changed on one client, the server is notified, but the other clients only find out eventually. And so, for instance, here is this example I showed you earlier. And eventually, this client says, oh, maybe I ought to ask the server, is F1 still at version 1? At that point, the server says, no, here's the new data, you update your cache, and now you're good to go. So there is this period of inconsistency allowed in the NFS caches, which can be a little weird. But it's sort of a low overhead thing. You got to poll periodically. Okay, and I'll tell you how this. Let me give you an example of how this manifests. Suppose that I've got one server I'm logged into from two different machines, and one of them I've got my Emacs or VI or whatever your favorite editor is, and the other one I'm using to compile. And I've just made my edits, and I've saved them out, and I go to the other one to compile, and what happens is some of the blocks are updated and some aren't, so the compile fails in a really weird way because you've got part of the changes. Okay? And that used to happen to me all the time when I would be editing on one and switch over to another. So the newer versions of NFS are much better at hiding that from you, but it's still potentially an issue. Okay. And the other interesting question is, what if multiple clients write to the same file? In NFS, you can get either version or parts of both. Now, before you say, wait a minute, that's just too weird, let me point out something. If you actually have two processes running on one operating system and they're both writing the same file, what happens? Well, you get some interleaving of the writes, right? Now, the fact that the buffer cache is shared means that you won't get this weird scenario where something's written and you never get a chance to see the other thing. But there still is this interleaving that's sort of by default in most Unix versions of the operating system. The only way you get around that is with, how do you prevent weirdness like that? That's right, you can do copy on write. What else? Locks. That's right. Good. Okay. So, what sort of cache coherence might we want from a file system like this? So here's a good example. We start with file contents A, and now client 1 reads the file and then writes B into the file, and then client 2 is reading, and depending on when the read starts and completes, it might get A or it might get parts of B having been written. And then it goes to write C, and notice, that it might read parts of B or C. So this seems like a pretty crazy kind of scenario here, especially since it depends on how your writes overlap the blocks of the file system, because the blocks are the things moving back and forth. Okay? And so what would you actually want? Well, you might want things to behave as if everything's on the same system. So if a read finishes before a write starts, you always get the old copy. If a read starts after a write finishes, you always get a new copy, and so on. And for NFS, the problem is, because of this, for instance, 30-second write thing, if a read starts more than 30 seconds after a write, then you get the new copy. So that's a little weird. Okay? But it's in there. Why? Why does NFS do that? They do that for performance. Okay? So some pros and cons. So the pros of NFS is it's really pretty simple, actually. You're just doing a block storage back and forth. The cons here is sometimes it's inconsistent, and it really doesn't scale to a large number of clients. So imagine that every client is polling. Is this still good? Is this still good? And if you've got 1,000 clients in one server, that sounds bad. right? You're overloading the server purely with consistency traffic. So that could be a problem. So I wanted to give you one alternative here, which is the Andrew file system. So this was developed at CMU and in the late 80s. And basically it's a pretty interesting file system. It's turned into DFS, commercial product. The basic idea here is quite different from NFS. So the idea is the client registers callbacks with the server to say, I am currently got a copy of file X. And so when things change, the server tells every client that has a copy, hi, it changed. Okay, so that's first of all not stateless, right? The server definitely has state about the client in this scenario. There's no polling bandwidth, which is nice. And the other thing it's a little more subtle but also quite interesting is writes only get propagated on close. So when you open a file, you freeze the copy at that point, you operate on it, you can read and write it all you want, people could be writing the file, it doesn't matter, you keep seeing the version that you started with, and when you close, then your changes are propagated as a whole. The great thing about this is now you've done a consistent change. Okay, all of the writes I made are consistently reflected to the server. And the other thing that AFS had, so that's a different API. The other thing that AFS had, which is interesting, is whole files are actually cached on the local disk, not in the memory of the buffer cache. So as with NFS, you would be buffering back 4K pages with the server. In Andrew file system, you buffer big chunks of the file on your disk, and so you can have much larger cache. You can have a cache that's the size of your disk rather than a cache that's the size of the DRAM, and that's a much, in many cases, much better scenario. Okay? And everybody who has the file open sees the old version and doesn't get a newer version until they reopen the file. Does everybody see the difference in semantics there? So NFS, you open the file, and you immediately, every read is sort of potentially gives you updates that other people have made. AFS, when you open the file, you don't get new changes until you close and reopen. Question? Yes?
So we say that server is immediately telling everybody with an old copy about changes, but everybody doesn't get newer versions until they reopen the file.
That's right.
So when the server tells me there's new information about a file, is that just like a courtesy notice to me?
What it really does is it makes sure that after I'm done with the file, I throw it out and have to re-request it. So it allows me to make a decision whether to go back to the server at all. If I open and write the file multiple times and nobody's changed it, there's really no reason for me to even communicate any further with the server. So AFS, by the way, was really designed in the 80s for having as many clients as possible per server. That was kind of their metric that was important. And they really wanted to downsize the traffic on the server. And so this combination of callbacks and these session semantics were really targeted at making sure that I didn't stress the server. And by the way, I think the nice thing about these session semantics is they're really clean, right? I know what I'm getting. I open the file, I get a snapshot, I mess with it, when I'm done writing, I store only back to the file, to the server when I close. And so everybody sees a consistent snapshot of the data. Okay? Good. And by the way, this, Andrew, so data is cached on disk instead of memory. All right, I mentioned that. If the server crashes, you lose all the callback state. So this is kind of unfortunate relative to NFS. When the server comes back up, it's actually got to go through and reconstruct the callback state. So there is much more work involved in rebooting a crashed server. And by the way, I guess I didn't write this, but the Andrew file system was the one I mentioned earlier that had the global namespace that everybody was in. And so in principle, every server that you pulled up on the net basically had a space in the global namespace. And that was kind of interesting aspect of this. All right. So the pros relative to NFS is there's less server load. The disk is the cache, so you can have more files cached locally. Callbacks mean you don't have the server involved if the file's read only. And In both AFS and NFS, ultimately the server is the main bottleneck because there's a single server here. Now, in AFS, there actually was a little bit of an optimization to have many read-only partitions, but the moment you allow things to be written, then the server becomes a bottleneck. Okay. Questions? Yeah.
Say you have two files open on two separate clients.
Yep.
Actually, one file, but then two versions open on two separate clients.
Yep.
And say the first one writes, and then the second one decides not to do anything about the server telling it that it's already been written, and then it decides to write itself. So what's going to end up on the server?
So let me make sure I understand. So you have two clients. They're sharing a file or they're not sharing a file? And so when they're sharing a file, basically the way they find out that a file has changed is, they have to be, the way they get updated data is they have to keep reopening the file. If there's a protocol for that you want for communication, then you might have a separate locking or communication protocol that notifies them that things have changed if that's required for your application. But if client A is busy opening, writing, closing, opening, writing, closing, client B will get A's updates. When it opens, it'll get all the updates the server has seen up to that point.
Well, what if it's like open before and then closes after client A?
Well, if it opens before client A opens and modifies, and it closes after client A closes, then B will not know anything about the change until it opens again. That's part of the semantics of this. Okay? Good. So you have to, if that's going to be a problem with your application, you have to program, you have to set up some external mechanism to deal with it. I wanted to say a little bit about how NFS is implemented, for instance. So notice we actually have the system call interface. We have a VFS layer, which I want to tell you about right now, and then underneath the VFS layer, we potentially have many types of file systems, one of which is NFS. NFS uses an RPC system called XDR to communicate, and so at the server side, we sort of have the lower part of the stack. So the virtual file system layer is a very interesting thing that was also developed by Sun Microsystems originally, and the idea is that the system call, like this copy, whatever, goes through the system call interface to VFS, and VFS, depending on which file system you're talking to, figures out how to direct it to the right file system driver. And this is essentially not only why I can have both NFS and ext3 on the same file client, it's why I could have ext3, NTFS, and NFS and MS-DOS or whatever, all on the same client, because VFS lets me deal with all those different file systems with all their different properties. Okay, and so VFS is a virtual abstraction similar to a local file system, but it's actually between the system call level and the actual disk drivers and file systems. And VFS allows the same system call interface with all these file systems, which is useful. And by the way, in Linux, VFS actually stands for Virtual File System Switch. I don't know why they decided to do that, but Linux likes to be different about things, so there's an extra S in there, by the way. So this is called VFS. This is what Sun called VFS. I guess it's all good because it's all VFS. Maybe this is VFSS. I don't know. For instance, just to say a little bit, the VFS common file model in Linux, basically you have 4 primary object types. So there's actually a super block type, an inode type, a directory entry type, and a file object. And there's actually no directory object because in Linux, directories are files. And so what's interesting is if you're implementing a new file system, you actually typically have to shove the ideas of your file system into the way Linux fast file system thinks of things. And so it might be that even if directories are not files, you have to make them look like files to that interface, or you may want to make it look like there are inodes or whatever, even if you just have a FAT file system or whatever. And so part of making this work for a given file system is you have to sort of figure out how to adapt your file system to the way this VFS layer expects things to be. And if you take when I treat the advanced OS class, we actually build a file system in VFS, so you get a chance to look at that. But now, for instance, the write that you do at user space actually goes through VFS and turns into a syswrite, which then gets directed to the particular file system, which eventually gets to the disk. So what we did when we talked about this was we sort of talked as if VFS wasn't there when we were talking about file systems earlier, and we sort of said, well, write gets directed into the file system. In fact, it kind of goes through VFS and then is directed to the right file system. Okay. I don't want to say any more on this unless there are any questions. And you can learn how to use VFS. So that's a layer. You could go to your friendly neighborhood Linux source code if you're feeling particularly like you want to build a file system, and you can learn how to use the VFS layer. Okay? I can tell there's some of you that can't wait to do this when you get home. You should do checkpoint number 1 for project 3 first. Okay. So now I want to do, let's take a brief break, and then I want to do one last topic before the day is done. So let's take a break. No. The version that the client was already opened and sees is the first version. So think of the point when you do an open. It's like snapshot exactly at the point I do an open, and that's all I see until I close it up again. Right. That's a good point. That's an interesting thing. You're going to have a situation where merging is required.
But it's very serializable if you do it that way.
Perfectly.
Yeah.
Well, it's actually closer to what's called snapshot isolation.
Yeah.
So you could actually come up with something that's not serialized.
You both read and then you make a right. We talked earlier this semester because I need to schedule an alternative final exam time.
Okay, can we talk after class?
We can.
Great. Okay, so I want to change gears here. So let's talk about key value storage. Yes, you're working on kind of a key value storage project, but it's not like you needed a lot of what I'm going to say here to get going on it. But what's interesting about key value storage is it's everywhere these days. And the idea really is that you have systems that store a combination of key and value tuples. And the interface is simple. Put key comma value, inserts a value, and then get with the key gets the value back. Okay, so this is basically, put says put this value associated with that key, get gets the value associated with the key. Sorry about that weird wrap. And it's sometimes considered a simpler but more scalable database. Okay, because the only thing you can do is map keys to values, and that's all it does. Now, what's surprising maybe the first time you hear about this is you might say, well, wait a minute, that's so simplistic, it's no way that that's useful. because I think of databases, I can have columns and many rows, and I can do, But surprisingly, key value stores are everywhere. Amazon, for instance, your customer ID might map to your profile. In Twitter, your user ID might map to your profile. iCloud or iTunes, the key might be the name of the song, and the value might be a movie or the song. And even further, Amazon actually has really interesting key value storage databases. We talk about DynamoDB in 262. It's a fun paper. Simple Storage System's another one. Bigtable is Google's version, and that's a huge infrastructure inside Google. Cassandra is a public domain key value store that's used by lots of cloud applications. Memcached, which you may or may not have heard of, but it's pretty much provided as a distribution with all Linux, is not on disk. It's an in-memory version. There's eDonkey, eMule. There's all these things that are key value systems. Okay? So what I want to say a little bit more about the key value store in general is one of the principles of key value stores is it's not a hash table, because that's the obvious implementation of a key value store is you build it in a hash table. Usually when you say key value store, you mean a distributed hash table. Okay, so let's get that out of the road here. So the main idea is you partition the set of key values across many machines, and so the keys are spread across a lot of machines, and that's going to be where scalability comes from in typical key value storage systems. And the challenges are, for instance, what happens if the machine that has your range of keys that you care about goes down? You're out of luck, right? Unless there's something interesting in there to handle machine failures. Scalability, so we want to make sure, because typically the systems we're talking about, imagine Facebook or whatever, are so large, we need to easily scale to thousands of machines. And not only that, but we need to be able to easily add new machines whenever we want. Okay, and then consistency is a little tricky. So we already said with NFS, you saw that weird consistency where I see parts of somebody's writes and parts of somebody else's. You can imagine in a system with thousands of machines, the consistency is going to be pretty tricky. And then, of course, what happens if the systems are very fast or slow or behind slow networks or whatever, and we somehow want to deal with that heterogeneity while providing transparency. There's that word that really means opaque again, okay? So thanks, by the way, for whoever actually put that post up on. That was pretty funny, the wiki post on transparency. So some key questions, no pun intended, are, when you do a put key comma value, where do you store the new key value tuple? When you do get, where is the value stored? Okay, those are some obvious ones. And then we want to do this all with while providing fault tolerance, scalability, consistency, and so on. You can easily imagine that CAP theorem might start creeping in on this under some circumstances. But for instance, the simplest thing you could imagine is a directory-based architecture where a single node maintains the mappings between keys and machines, and all that happens when I say put, key 14, value 14, I send it to the master. The master looks that up and sends my put onto the proper machine, which then does the put. Okay, and maybe the master keeps a copy along the way. Okay, but in this instance, we're purely using this as a lookup service. So, basically having a node that maintains this state maybe is going to become a bottleneck pretty quickly. But for instance, if I do a get, then I do the same idea. The get sort of is forwarded back through the master and on. And so what's interesting about this is not only am I involving the master in my lookup, but I'm also involving it in routing my data back. And so now maybe this master directory is starting to become quite a bottleneck. This idea of having the master, whatever it is, relay all the requests is typically called a recursive query because I'm recursively working my way through the network. And you'll see in a moment how that at the very end of this, you'll see how recursive really comes out into play. Another method is essentially iterative, where the client who's sitting right here does a put, and what comes back from the directory is, okay, if you want to do a put for that key, you got to talk to N3, and then you go ahead and do it. All right, and why is this called iterative? Because I'm iteratively, first I'm looking things up, and then I'm doing the operation. The second one is much more akin to what we've been talking about in this class already, which is there's a DNS lookup, right? You look up who's storing the key, and then you do the resulting put. And then, of course, when it comes to actually doing gets, I might do it this way as well. Okay, and so now the master is no longer in the critical path of the data, so maybe that's a good thing. Okay, and so this trade-off between recursive and iterative is something that often comes up into play in a key value store. And so this iterative versus recursive, we can sort of see advantages and disadvantages. So the good thing about a recursive query is it's fast, because typically we're doing a small number of hops through the network, right? We go to the directory and then to the thing and back, directory, the storage server and back. The consistency is probably easier to maintain because everything goes through one single point like the master. And so if I want to make sure that all of the updates appear in a certain order to everybody, that might be easier with a recursive query. The disadvantage, of course, is it's a scalability bottleneck because every value goes through the master. And if your value is a movie, that starts becoming a problem. Okay? The advantage, so what about iterative queries? So the advantages are more scalable from bandwidth, but boy, it's potentially a lot slower, harder to enforce data consistency, and so on. So this trade-off between iterative and recursive basically goes through pretty much any of these systems when you start looking at their implementation. Now let's talk a little bit about fault. Is everybody clear on that difference? Okay. So now we might ask ourselves about fault tolerance. And so the way we get fault tolerance is we need to replicate. It's the only way to get fault tolerance. And so we can put replicas on different racks, or ultimately, if we're talking about in the wild of the internet, on different in different countries or whatever. But let's start with the simple idea. And so in this case, I go to do a put, and the master actually has multiple nodes associated with that key, and it tells me that. And so then I can go ahead and do those puts. Where I take the N1, N3, and I send that along, and this is a recursive style put, which I can also do in the following way, like this. Okay, so there are many options, and you can, by the way, the only reason I'm going through this quickly is you can see, you guys hopefully can come up with all of these different topologies of how I could forward values on through the master and so on. Okay, and so a lot of the interesting questions about how do I implement these things come around to, how do I make the master scale, and what kind of communication pattern do I do, and what happens under failure? Okay. So how do we get more scalability? Well, for storage, we just add nodes. That's easy. How do we get scalability with more requests? Well, maybe we come up with some scheme where we can serve the requests from all of the nodes on which a value is stored in parallel. Okay, that sounds good. Maybe the master can replicate a popular value on more nodes as a way of getting more scalability. So if you have some video, like how many people are following the Warriors? A few of you, maybe? Not so. Oh, wow. Okay. Boy, they're hot. Anyway, so if you have some popular sporting event or something, you could imagine it being replicated on more nodes to get scalability, and with an iterative query, things are going well. You could get much more bandwidth out of it. But the interesting thing that comes into play in all of these is how do I scale the master or the directory? And, okay, we could replicate it, but now things are getting complicated, right? I've got a replicated storage system. I could partition it so different keys are always served by different masters. And then the question is, how do you partition it? Interesting, right? And so another reason that I might want to partition is load balancing. So I want to make sure that if I have many keys and I have many servers, I'd like to balance the load over all the servers. And I might even want to preferentially insert values on nodes that have more storage available. And so then, of course, all of these queries come up. What happens when I want to add new nodes? You can't insert new values only on the new node because the new node might crash right away, or many other things. I might want to move values from heavily loaded nodes and so on. And so this gets interesting. You might ask a question, when a node fails, what do? I'd like to put its load on other nodes, etc. So is everybody starting to see the space of design here? It's kind of interesting, right? I've got lots of nodes, and something as simple as a key value store, I'd like to figure out how to use all those nodes well, use their network bandwidth, use their disks, and cause my data to stick around. And this is a fascinating general topic. There was, for the whole decade of the 2000s, peer-to-peer research was a really hot topic, okay? And, you need to make sure that values are replicated correctly to get consistency, and this gets a little interesting because, for instance, if I'm going to replicate a value on more than one node, how do I actually know it's happened? Well, I could wait for an acknowledgement from every node, but maybe that's slow. What happens if a node fails in the middle of what I'm replicating? Well, then maybe I have to pick another node and try again. What happens if a node is really slow, so I think it's down, but it isn't actually? Then what? Slow everything down? Okay, so these kind of get a little complicated. It's interesting, right? So in general, when you have many replicas, the puts are slow, the reads are fast. Everybody see that? Why are the puts slow? Because I got to make sure everybody gets it. Why are the reads fast? I have many choices of where to get it from. In fact, I could even ask multiple of them at once and get back the combined version. Okay, now I wanted to show you an interesting little problem here. So let's suppose we have two things are updating data, and they're both putting a value to the same key. So here's one, and here's another one, the reds and the greens. And I apologize to anybody who might be colorblind. But here's an interesting problem. So we're replicating, and because of the way this worked out, the master happens to send the put of K14s, put the green guy over here and the red guy over here, and then swaps the two of them because of network ordering or whatever. And now the interesting question is, what's the last value that's on the left and on the right? Maybe on the left, the last value is the red one, and on the right, the last value is the green one. And now, even though we in theory have two copies, they're both different. Just because network ordering. Okay, so the moment you start thinking about replication, you got some problems with consistency. And I did want to say a little bit about many consistency models. Okay, you can have things like atomic consistency, which makes it transparently looks like a single disk. You can have eventual consistency, where they keep exchanging information and eventually everybody agrees on the same value. There are lots of others. You can get casual consistency, sequential consistency, strong consistency, inconsistent consistency. Oh, I made that one up. Lots of options. And by the way, eventual consistency seems to be the thing that people mostly settle on. And so I just wanted to show you one option, which is pretty popular these days for systems that are key value stores, and that's quorum consensus. And the idea is we improve the put and get operations a little bit with the following idea. We're going to replicate n replicas, and put is going to wait for at least W acts to come back, and get is going to wait for at least R acts to come back, such that W plus R is greater than n. Why is that useful? Why is W plus R greater than n help us in consistency? Yeah.
Because if it was successfully written to W of the things, then if you get R gets, then you know that it has to be consistent.
Why? Why?
Because if all of your W is written, and then there's fewer than R that are like different.
Yeah. So the real answer here is if W plus R is greater than n, there's at least one node that overlaps the two, and therefore I always get the latest value. Okay? And you might even ask yourself, well, why does it work? There's at least one node, and why might we want W plus R to be greater than n plus 1? Well, if there's one that overlaps and that one crashes at the wrong moment, maybe you want two of them, right? So this idea of quorum consistency is used now in systems like Cassandra and DynamoDB, and a bunch of systems that are key value stores. Now the downside of this, of course, is you're an application writer, you got to pick W, R, and N. So what actually happens? Well, N is always 3 and W and R are 2. Okay, is what often happens for people because that's kind of the default they use. But you could imagine that W is equal to N and R is 1. Might be a mode where you don't write very often, but you want to do really fast reads. Okay, that might be a good combination where reading is the thing you do fast and frequently. Okay, so here's an example where I've got N equal 3, W2, R equal 2. And I assume I'm going to put on N3 is going to fail. Notice what happens here. I go to try to do my writes. I get a failure. I only get ACKS back from 2. Oh, good. I got ACKS back from 2. Good to go. And so now when I go to do my read, maybe I accidentally ask N3, but I also ask another one. And as a result, I actually get my updated data. And so this works. Okay? And in the background, these systems like Cassandra basically run what's called an anti-entropy protocol in the background. What anti-entropy means is they keep exchanging information, getting each other up to date, and so this server N3 will eventually get all of its data up to date when it comes back. All right, good. So how do we scale the directory? This is the last little thing I want to say before we go. So the directory contains many entries equal to the number of key value tuples, and you can imagine that if you've got too big of a key value store, the directory is just toast. And so what do? You do something called consistent hashing. And the idea is pretty fun and simple. It's basically associate to each node a unique ID in a unidimensional space. And I just want to show you a picture. So all of these servers are storage nodes, and they all have a unique space place in this ring, which is 0 to 63. Now why 0 to 63? Only because I said the number of bits M was 6. In reality, the number of bits is the size of a hash, so it might be 256 is a good number. And so, and then you can sort of say, well, node 8 basically maps all keys from 5 to 8. Node 15 maps everything up to 15. Node 20 and so on. And as long as you have a good protocol, you can say, well, for every key I want, the directory that I'm interested in is stored on this node 15 because 14 is, node 15 here is the first real node on the ring for 14. So this key 14, if I would find its place on the ring and I would go forward, the successor node that would store 14 is 15. Okay, now you might say, wait, well, that sounds awful. Why does that help me? And the reason is that there are these interesting systems like Chord, which take a ring and allow nodes to join and leave and keep track of who their successors are and their end successors. That's called the leaf set. So you have to trust me on this, but there's good protocols where a new node comes up and it finds its successors and predecessors and ties itself into the ring. And now the way I can route from source to destination is, and these red things are what are called fingers, I go across the ring as far as I can. That will have its own fingers and leaf set, and then I can make another hop and so on and make a hop to the destination, and then from the destination it goes back. There are really good scalable protocols for doing this. One is called Chord, and notice how that was a log number of hops with a recursive query that basically got me to the directory here for a given key I was interested in, and that would also potentially store the data and send it back. So this is how you could replicate the directory. Okay? So all of the peer-to-peer research, and we could talk more about this if people were interested in our final lecture, but there's lots of really interesting protocols that are resilient to any of these nodes failing at any time. You make sure the replicas are all on the leaf set. Pretty interesting, stable stuff. But that's all I needed to do for now. I did want to finish up by saying, look, DynamoDB, they actually build systems like that with rings that actually talk about service level agreements for sort of I can, get to 300 millisecond request in 99.9% of the time, and Amazon actually does that. All right, so in conclusion, we talked about distributed file systems which provide transparent access to files stored on remote disks. We talked about interesting cache consistency issues with NFS and AFS. We talked about how remote procedure calls make it easier to program these systems. We talked about the virtual file system layer for many different types of file systems in the same system. We talked about key value stores and put and get. And then next time we're actually going to start talking about some interesting things to do with security. So I will see you guys on Wednesday.